Hello, this is Dr. Muhammad, and this is another video under the matrices, and I'm going to talk today about the second part of the linear homogeneous system, and I'm going to talk today briefly about what we have explained before, and I'm going to give some examples and in-class assignment for this topic. Okay. Now, before going into the details, I'm going to talk about the trivial and non-trivial solutions for the systems. But before going into this, I'm going to give a reminder of what we have explained in the previous video, so that it will help us to understand about the trivial and non-trivial solutions. So first of all, in the previous video, I have mentioned about some important hints that we need to keep in our mind. First of all, if you remember, we were talking about the free variables, and we were talking about the relation between the A reduced times x equal to 0 and the coefficient matrix times x, that they are equivalent and they are having the same solutions. And we said that if we could find AR from our original coefficient matrix, then it will be very easy for us to solve the homogeneous equation. And we mentioned that whenever we have this AR, which is the reduced echelon form, we can read directly from this matrix the number of the free variables besides the solution dimension of the system. Okay, because they are, as we said, they are like synonyms. So free variables and the dimension of the solution, they are the same. So this is something that is very important for us. We need to keep in our mind that AR contains, or AR, the free variables occur in columns of AR that contain no leading entry of a row, as we have mentioned before. Okay, so we have the free variables, we can read it directly from the reduced matrix. So this is number one. Number two, I have mentioned about this theorem, which is already something that is taken for granted for us, and you can verify it by yourself if you want. But it is, as we said, if we have a system which is its coefficient matrix n by m, then the systems ax equal to 0, which is the original system, and the reduced system, which is I said here, okay, they have the same solution. How we can verify this? Simply, you can just do as we have done in the previous examples. Just try to reduce the system and get the solution, and then back substitute in the original solution by x1, x2, and x3 that you have obtained here, and substitute in the original system, and check whether that the right hand side is going to be 0 or not. This is the only way and simplest way. If you want to go into the details, you can find it on the book, but it is easier for you to do what I have mentioned. Another thing, which is Theorem 7.12 in the textbook, and already I have mentioned it before, which is talking about the solution space of a homogeneous system. And we said that if we have a coefficient matrix that is n by m, then the set of all solution of the original ax equal to 0 system forms a subspace of Rm called the solution space of this system. Okay, so we are talking here about the solution space. What is the solution space? What is the dimension of the solution, as we said before? Okay, the dimension of this solution space is m, which is the number of columns in the coefficient matrix, minus number of non-zero rows in AR. Again, we are talking about the AR, as we said, and the number of non-zero rows. Okay, if we have 3 or 4, if we have like 2 non-zero rows in a 3 reduced matrix, then the number of non-zero rows, which is considered to be the rank of the original matrix A, we should like subtract it from the original number of columns of the original matrix, and we can get the dimension of the solution. What is the meaning of the dimension? Yes, the dimension means that the number of variables or the number of free variables, which is this one. Already we have explained it before. The number of the free variables that is going to define, or we can call them like the independent variables, where that other variables, other x1 and x2 and x3, they are dependent on them, okay? Which is the same as m minus the rank of A. We said that rank of A and the number of non-zero rows of A they are the same, okay, from the previous videos, okay? These are the 3 main hints that I want to keep in our mind before going and indulging into the next part, which is related to the trivial and non-trivial solutions. Okay, now let's go here and understand what is the meaning of this. A homogeneous system always has at least the trivial solution and may or may not have non-trivial solution. Now stop at this sentence. Stop at the sentence and let's understand it. We're talking about the homogeneous system, right? Where that it is in the right hand side, we have zeros. Always, this means that always it will have at least trivial solution. Trivial solution means that all variables x1, x2 and x3 and so on, trivial means that all of them, they are like zeros, for example. This means that the system is not working. It is trivial solution. It is trivial solution. So any homogeneous system always has at least. So trivial solution is always there. Okay? Trivial solution. The solution that will not help us in obtaining or making the system to work, which is, as I said, x, all of the x, for example, equal to 0. You're going to find something like this. So we have one at least trivial solution. And in the same time, this system may or may not have non-trivial solution. The non-trivial solution is the healthy solution that we're expecting. We want the system to be in work. So we have x1 and x2. They are having values that is making the system to work. Right? So again, remember, homogeneous system at least always has at least a trivial solution and may or may not have non-trivial solution. So we are searching for this non-trivial solution. I mean here, this one, okay? And we do not want this trivial solution. We want to get the non-trivial solution. Okay, let's go to this theory, which is 7.3. Let A be n by m. It is again coefficient matrix. Then the homogeneous system, which is ax equal to 0, has a non-trivial solution if and only if. So now we are like going closer to our non-trivial. We want a kind of rule. How we can say that this system is having a non-trivial solution or not. We want to understand this. We want to know it from the beginning, right? So we want to put a rule for this. So if we have A, which is the coefficient matrix, and it has this dimension, which is n by m, then the homogeneous system has non-trivial solution if and only if. This is the rule. M minus the number of non-zero rows, which is what here? This is what we call it? Exactly. It is the rank of A. Rank of matrix A, the original matrix A. Fm, which is the number of columns of the coefficient matrix, minus the number of non-zero rows of the reduced matrix of the coefficient matrix. If it's larger than 0, then our system has a non-trivial solution. That's very good. Now it adds to our knowledge the importance of the reduced matrix, how much that it is really important for us to know. It gives us a lot of information. So it would, from AR, if we know the ranking of A or the number of non-zero rows in AR in the reduced form, and we, of course, we know the M, which is the number of columns of our coefficient matrix, simply we can judge the system whether it has a non-trivial solution or not, which is may, as we put it here, may or may not. Okay? Okay. So now this is our case. Now this is the simple condition for a homogeneous system to have a non-trivial solution. This is a very simple condition for the homogeneous system to have a non-trivial solution. Now, a linear homogeneous system with more unknowns than equations always has non-trivial solution. Now let's go deeper here. If we have a linear system, linear homogeneous system with more unknowns, do you remember what is the meaning of more unknowns? Which is x1, x2, x3, and so on. More than more unknowns than equations. So if we have like first equation, second equation, third equation, and we equate it with 0 every time. So this is, we have 1, 2, 3. This is the number of the equations. If we have the number of unknowns to be more than the number of equations, let's assume that we have x1, x2 until x4. We have 4 unknowns, but we have 3 equations. This means that we always, look to this word, always has a non-trivial solution. So we're going to have non-trivial solution for us. Okay? So this is something that we need to keep in our mind whenever that we are solving. Okay. So this small condition that we have had here implies that AX equal to 0, this system, has only the trivial solution, take care, has only the trivial solution exactly when M minus the number of non-zero rows of the reduced matrix is 0, right? And this is right because we are talking about that, about this, we mentioned about this here, and we have mentioned about this here. In particular, when A is square, then M equals to n. If we have this matrix to be square matrix, n equal to m. And this occurs exactly when n by n matrix AR has n non-zero rows. The reduced matrix is going to have n by n. This means what? Which in turn happens exactly when AR equal to in, the identity matrix. It is going to be like this, for example, 0, 1, 0 here, 0, 0, 1. Okay, so this matrix is going to be the reduced matrix. This means what? The number of non-zero rows, which is going to be here 3, for example, and we have 3 equations, right? That's right. And we have 3 unknowns, for example. So in this case, 3 minus 3, it is going to be like 0 in this case. Okay? So this means that we are having trivial solution in this case. Has only the trivial solution exactly when m minus the number of non-zero rows of the reduced matrix is 0. We're going to see an example for this, so do not worry. You are going to understand it clearly after a while. So if A is n by n, then AX equal to 0, which is the homogeneous linear system, homogeneous system, has only a trivial solution if and only if AR equal to IN. That's what I want you to remember and memorize. Whenever that we reduce A in order to obtain the AR, if this AR, we found it IN, which is the identity matrix, this means there is a problem here and we are falling into the trivial solution. The system has a trivial solution. Okay, so what is the outcome of here? Okay, we said that. So we can put it in a very simple form. I want to clean everything here. So shift erase. So the very important thing is non-trivial solution is here if this condition applies. M minus number of non-zero rows, or M minus the ranking of A larger than 0. So this is the most important thing. This means non-trivial solution is there. Okay, what about the trivial solution? Trivial solution is here. If A r equal to in, this means that we are having trivial solution. So remember these two things. Non-trivial, when we have this equation applies, m minus the ranking larger than 0. But if our AR, the reduced matrix, equal to in, this is a problem. We are facing the trivial solution case. Okay, let's have some examples to understand what we are talking about. Okay, now let's solve this. We will solve this system, as you can see here, minus 4x1 plus x2 minus 7x3 equal to 0. And also we have here x1, x2, x3. So we have x1, x2, x3. Number of unknowns, we have 3. So the number of unknowns are 3. Okay. And our coefficient matrix from here, it is A. Just we extracted the coefficients and put it here. And when we worked this AR, we want AR to check the two other conditions that we have mentioned in the previous slide. So we found that AR here, you can check it by yourself. Check this AR, you're going to find it. It is giving you something like this. It is the identity matrix. 3 non-zero rows. So now let's apply our method, which is m minus rank of A, which is m, we have m, okay, m, it is the number of what? Of columns of this coefficient matrix, 1, 2, 3, we have 3 minus the rank, 1, 2, 3 is 3 minus 3 equal to 0, right? So this means that here this is 0, and the reduced matrix in general, it is the identity matrix. So it brings us to back to this equation. Do you remember AR equals to IN? Okay, this means that 2 actually they are fulfilled here, because this one is fulfilled and also this one is fulfilled. M minus 1, it is not larger than 0 in our case, so we are not going to have the non-trivial. We are going to face the trivial case. So here this is what happened. That is AR equal to the identity matrix. Then we are going to end up with what? x1 equal to 0, x2 equal to 0, x3 equal to 0. From where we got this? You just put the system, which is AR times x equal to 0. AR here is what? This matrix. So 1, which is reading from here, if we multiply it, for example, by x1, x2, x3, and equate it with 0, then you're going to find that 1 times x1 and the other two are 0 equal to what? 0, which is the first one. And here x2, which is this is the only one, times 1 times x2 and the other x1 and x3, they are 0 equal to 0, which is this one. And x3 the same, equal to 0. This is trivial solution. This is the trivial solution. Therefore, the system has only the trivial solution. This can also be seen from the reduced system, which is, this is the reduced system. I mean that after putting AR equal to ARX equal to 0, you're going to find that the equations are going to be set in this way. This is trivial solution. Okay, now let's go to the next part. So we will use, in order to solve this example, we are going to use the fact that AX equal to 0, our system, has the same solution as AR equal to ARX equal to 0, which is the reduced system. They are going to have the same, solution. And the fact number 2 is the solution of the reduced system can be read by inspection from the reduced coefficient matrix directly. That's right, that's very true. We are not going to solve the reduced system. No need for this. It is easier for us to inspect this matrix, which is the reduced matrix. Okay, it is better for us to inspect it. Okay, now let's apply these two facts in a very simple example to see it. We have this system, a linear system, homogeneous equation, x1, x2, x3, x4, and we have here x2 and x3 and x4. So we can put the coefficient matrix extracted from the system. We have 1 and 0 for x1 here, and there is no x1 here, so it is 0, and also for the x2. So we have, this is for x1, this is x2, this is x3, and x4. This is A. Work out the reduced matrix. Please do it by yourself. We're going to find that AR, the leading entry here, the leading entry here. So we have 1, 2, so we have x1 and we have x2 considered to be dependent, and we have x3 and x4. They are going to be our free variables, right? They are going to be our free variables because they are the two columns that do not have the non-zero or the leading entry. Okay, so first of all, the rank of our matrix, which is the rank of A, equal to what? The number of non-zero rows in the reduced matrix, which is 2. Okay, so this our general solution is going to have m minus 2, which is the ranking of A, equals to this m. How much? Exactly, we have 1, 2, 3, 4. We have four columns, so it is going to be 4 minus 2, which is 2. We have two arbitrary constants, which is going to be x3 and x4. Said and mentioned about this. So the dimension of our solution is going to be 2. This dimension, this is the dimension of the solution space. From the reduced system, we read that this is the reduced system directly. Read, so I'm going to clean this up. Now from the reduced matrix, this one, the leading entry, it means that x1. And then we have x3, x4. Put it in the right hand side. So x1 equals to, take care, we are going to take the negative sign here, I mean the opposite side, equals to minus x3, as you can see it here, plus x4, because we have minus 1 here, so plus x4. And reading from here, we have this as 0, so we do not have x1, we have x2 equals to x3 minus x4. x3 minus x4. So this is our solution now. Okay, x1 and x2, they are function of x3, x4, x3 and x4, right? As we were expecting that our general solution dimension is 2. Okay, so that's the case for us. Okay. Okay, so this system has a trivial solution or no? First of all, the identity matrix, AR, does it equal to I node in this case? I mean that the identity matrix? No, it does not. As you can see here, it's not identity matrix. So we have the non-trivial solution. And in addition, this non-trivial solution is going to be dependent on what is the dimension of our solution. It is going to be m minus rank. It equals to 4 minus 2, which is positive. Okay, so this means that yes, we are in the non-trivial solution space, and the dimension of this non-trivial solution space is going to be 2. What is the meaning of the dimension? Again, the number of the free variables, which is going to describe the other dependent variables. Okay. Now let's go to the form of the final solution. This system is solved by giving x3 and x4 any values. As we said in the previous video, you can mention about this. So our solution is going to be like in 2-column solution. We want it to be 2-column solution. Okay, so we can put it like this. We have x here, x1, x2, x3, and x4. x1 equal to what we have explained in the previous slide. x2 equal to the same, and then x3, it is going to equal to x3, and x4 equal to x4 as it is. But we do not like this way. We like to put it, as we said, it is 2-dimensional, then we need 2 vectors here. So we're going to put our free variables outside like this, x3 and x4, and we are going to give them a nicer name, like, for example, alpha and beta. It's only names, okay? It's only names. So, and we are going to say that this x3 times minus 1 plus x4 times 1 equal to x1, which is the right thing. x1 equal to these values. And the same for x2. The same, x equal to x3 minus x4, so x3 plus x4 times minus 1. So it gives you x3 minus x4, and x3 and x4, they are the same. That's the form that we need to have. And we call these as both are arbitrary numbers. Okay? And the final solution is going to be x equal to alpha and beta times the column vectors, as you can see here. Okay? That's the case. And let's have another example, and then I'm going to give you the in-class assignment. This is the example that we have. This is the system, linear homogeneous system, as you can see. We are going to solve it. First of all, extract the coefficient matrix. Easy for you to extract it from the system, and you're going to find it here. Then work out the reduced matrix AR. We checked it and put it as XR. This is the AR. Does it equal to the identity matrix? No. So we are having non-trivial solution. Okay. Looking to the leading entries, we have 3 columns for leading entries, but we have 2 columns that do not have the leading entries, which is x4, x5. Okay. So this means that our matrix here, it is 3 by 5. So the dimension of our solution is going to be 5 minus the ranking. The ranking here is 3. This means that 2. We are having 2-dimensional space solution. Okay? We are going to work the same as we have done before, and you are going to find that we are going to put x4 and x5 as alpha and beta, and the general solution can be rewritten in this nicer form, alpha and beta times the column vector. Okay, this is for the example. I think you are ready, very ready now to have the in-class assignment. Okay, now this is the in-class assignment. First of all, determine the dimension of the solution space and find the general solution of the system by reducing the coefficient matrix shown. Okay. Write the general solution in terms of 1 or more column matrices, as we have learned in the previous examples. We have like 1, 2, 3. Now you can look to these systems, stop the video, and start to work out by yourself. Okay? Work it out by yourself without looking to the solution that I'm going to show to you in the next slide. Okay. Now welcome back. After solving this assignment, let's take the first one, the first system. As you can see here, we are going to extract its coefficient matrix, which is something easy. I think that you have done it by yourself. And then reduced matrix. When we reduce the make reduction, we found that we have the identity matrix. Okay, this means what exactly? We have trivial solution. Trivial solution. It will not work for us. So there is trivial solution, which is x equal to 0 at the end. Then this system does not work for us. It has the trivial solution. Okay, so now we understand it from the reduced matrix. Now let's go to the solution for the second problem. This is the coefficient matrix. I hope that you have done it right. So we have, as you can see, it is 4 by 1, 2, 3, 4, 5. So it is 4 by 5. And work the reduced matrix. You are going to find it like this. And we are not having the identity matrix. So this means that we are, yes, we have non-trivial solution. And we have here x1, x2, x3, x4, and x5 seemingly to be our free variable, right? Our free variable. What is the dimension of this solution? It is going to be m minus the rank of A. M here, it is going to be 5, the number of columns in the coefficient matrix, minus the rank of A, which is the number of non-zero rows in the reduced matrix. 1, 2, 3, 4. We have 4. It equals to 1. And this is what we were expecting because we have only one column that does not have the leading entry. This means that our x1 and x2 and x3 and x4, they are going to be defined by alpha, which is, what is alpha? Exactly, it is x5. Okay, that's it. And you can get the values like this one. I hope that you have worked it well. If you want how to know how we have reduced this, this is the details. You can go through it. Okay, this is for the first problem. This is for the second problem, and this is all the row operations that we have done in order to obtain the AR and then the final solution for it. Okay, can go through it if you want by yourself, and you can find it in the PDF file. Okay, and now number 3. I hope that you have worked it well. I'm giving it like gradual complexity of work, and try to work by yourself because you are going to face something like this, okay, when you are solving, for example, in the exam. So now we have this system 1, 2, 3, 4 by 1, 2, 3, 4, 5, 6, 7. So we have 7 here. When we reduced it, you find that it is having like 1, 2, 3. So we have 3-dimensional space. Okay, so this means that our space of solution is 3. The dimension of our space of solution is 3. And then you are going to find that they are dependent on x1, 2, 3, 4. Then x5, x6, x7. They are going to be our free variables. So we're going to have alpha, beta, gamma for x5, x6, and x7. And the remaining you can put it and do it by yourself. Okay, this is the in-class assignment. I hope that this is actually the details of this one to get the reduced matrix from the original matrix. You can go through the steps here, and then you can get the detailed type of solution. Okay, now you are ready to have the home assignment. So now this is the home assignment. Please solve it by yourself as in the in-class assignment and try to work out the general solution. This is the end of this video. Thank you very much for listening, and I hope to see you in the next video. Okay.